Welcome back to Applied AI Engineer. This episode opens a brand new module, Retrieval Augmented Generation, the technique that lets a model answer from your own documents instead of guessing. Everything in RAG rests on one idea, embeddings, so that's where we start. Today we'll turn text into vectors of meaning, build cosine similarity by hand in NumPy, run a real semantic search over the Atlas docs, and see exactly when searching beats stuffing everything into the prompt. By the end you'll have a working search engine that finds the right passage even when it shares not a single word with the question. Quick continuity. Last episode we worked with long context, counting tokens, chunking a document, and learning the hard truth that the context window is finite and every token costs money. That leaves an obvious question: if we can't paste the whole knowledge base into the prompt, how do we find just the parts that matter for this one question? The answer is semantic search, and its engine is the embedding. So let's understand what an embedding actually is. First principles. To search by meaning, we need a way to represent meaning that a computer can compare. That representation is a vector, a list of numbers. Let's see how text becomes one. An embedding is a function that takes a piece of text and returns a fixed-length list of floating-point numbers. For the small model we use, 384 of them. Think of those numbers as coordinates. Every piece of text becomes a single point in a high-dimensional space. The model was trained so that texts meaning similar things land near each other and unrelated texts land far apart. So reset password and change my password end up pointing in almost the same direction even though they share only one word. Here's the picture. A piece of text goes into the embedding model, and out comes a vector, for us, 384 floats. That vector is a point in space, and its direction encodes the meaning. We'll run this on a small model that lives entirely on your machine, so there's no API key and no per call cost. The key property to hold on to: similar meanings produce vectors that point in similar directions. That direction is what we're about to measure. Here's our corpus, 8 short passages from the Atlas product docs, covering passwords, billing, security, the API, and so on. In a real system these would be the token-bounded chunks we produced last episode from your wiki and PDFs. Keeping it to 8 handwritten snippets means the whole search idea fits on one screen and runs in a second, while behaving exactly like the real thing at scale. And here's the embedder. We use sentence transformers with the model all mini-LM, L6, V2, small, fast, and fully local, so it needs no API key. We load it once, because loading is the slow part and encoding is quick. The embed function takes a list of strings and hands back an n by 384 array of float32s, one row vector per input. That's it, text in, real vectors out. Running it on to short phrases confirms the shape, 2 vectors, each of 384 dimensions, as float32. Those first 6 numbers are real coordinates straight from the model, not made up. On their own they mean nothing to a human, their power is entirely in how they compare to other vectors. So now we need a way to compare two vectors and get a single number for how alike they are. The standard way to compare two embedding vectors is cosine similarity. It's a beautiful little piece of maths, and we are going to build it from scratch so nothing is magic. The trick is to compare the angle between two vectors, not the straight line distance. Why the angle? Because a longer document might produce a longer vector pointing the same way, same meaning, different magnitude, and we don't want length to fool us. Cosine similarity is the dot product of the two vectors divided by the product of their lengths. That formula always lands between -1 and 1. 1 means the vectors point the same way, so same meaning. 0 means they're perpendicular, so unrelated. -1 means opposite. Here's the entire thing. Cosine is one line, the dot product, divided by the two magnitudes that NumPy.linear.norm computes for us. And there's a performance trick alongside it: normalize. If we scale every vector to unit length first, then the denominator becomes 1, and cosine similarity collapses into a plain dot product. We do that scaling once, up front, and every search afterward is just multiplication. That's how this stays fast even with millions of documents. Let's prove the maths behaves. A vector against a longer copy of itself scores exactly 1, same direction, length ignored, just as we wanted. A vector against a perpendicular one scores 0. And against its own negative, -1. Those three anchor points, 1, 0, -1, are the whole intuition you need. Now let's point this at real meaning instead of toy vectors. Here we embed 3 pairs of real sentences and score each pair. The first and third pairs are paraphrases, same intent, mostly different words. The middle pair is deliberately unrelated. If embeddings work, the paraphrases should score high and the unrelated pair should fall toward 0. This is the single most convincing experiment in the episode, so let's run it and look at the actual numbers. And there's the payoff, in real numbers. Reset my password versus how do I change my password scores 0.798, strongly similar, even though they share just the word password. The unrelated pair, password versus API rate limit, sits at 0.033, essentially nothing. And cancel my plan versus end my subscription, which share no content words at all, still scores 0.444. The model is matching meaning, not spelling. That is the entire promise of embeddings, demonstrated. Visualized in 2 dimensions, though remember the real space has 384. The query vector for reset my password sits at some angle. Change my password points almost the same way, a small angle, so a high cosine around 0.8. API rate limit points off in a very different direction, a wide angle, so a cosine near 0. Searching is nothing more than finding the document vectors whose angle to the query is smallest. We can embed text, and we can score a pair. Assemble those 2 pieces and we get a real search engine. Embed the corpus once, then for any query return the k nearest documents. Here's the search engine, and it's barely a dozen lines. In the constructor we embed every document once and normalize them. That's our index, built ahead of time. At query time we embed just the query, then take one matrix vector product, the index matrix times the query vector scores all 8 documents simultaneously. We argsort those scores, reverse for descending order, and slice off the top k embed ones, search with a single dot product. That pattern is the heart of every retrieval system you'll ever build. Look closely at the first query, I forgot my login. It shares not one content word with our top hit, which talks about resetting your password, yet that doc ranks first at 0.354. The model understood that forgetting a login and resetting a password are the same need. The second query, is my data secure, correctly surfaces the encryption passage. These are real scores from a real model run on this machine. That is meaning-based retrieval working. The full flow in one picture. The query is embedded into the same space as the documents. One dot product against the index scores every document at once. We sort, keep the top k, and return them with their scores. Notice again the headline result on the right. The password reset doc shares no words with I forgot my login, yet it ranks first. Keyword search could never do that, which is exactly the comparison we make next. It's worth proving, side by side, why we go to all this trouble instead of just matching words. Let's pit a keyword search against our semantic one on the same query. Here's an honest keyword search for comparison. We strip stop words from the query, then for each document we count how many query words appear literally inside it. More overlap, higher rank. This is essentially how classic search worked for decades, and it's still useful, but it has one fatal blind spot for natural language questions, which the next run exposes brutally. And there's the knockout. For I forgot my login, the keyword search scores 0 on every single document. The user's words simply don't appear in the docs, so it returns nothing useful. Semantic search, on the same query, ranks the password reset passage first. This gap is precisely why embeddings power modern retrieval. Real users never phrase things the way your docs do, and meaning bridges that gap where literal matching falls flat on its face. Step back to the strategy. Last episode we could stuff a single document into the prompt. But a real knowledge base is thousands of documents, far past any window. So when the corpus is large, you have no choice, you must retrieve a subset. And even when everything would fit, retrieval is still the right call. Fewer tokens means a smaller bill and a faster reply, and less irrelevant text means the model is far likelier to find the needle instead of drowning in hay. The rule is simple: retrieve the few chunks that matter, never paste the whole library. Side by side. On the left, stuffing everything. 10,000 docs jammed into the prompt, a huge token bill on every call, an overflowing window, and a model that loses the answer in the noise. On the right, retrieval, embed once, search by meaning, and send only the 3 to 5 best chunks. A tiny prompt, low cost, and a focused, grounded answer. Semantic search is the front door to retrieval augmented generation, and in the next episode we walk through it. Often you'll reach for a hosted embeddings API instead of a local model. Voyage, which Anthropic recommends as its embeddings partner, and OpenAI both expose the same shape: send text, get vectors back. They tend to be higher dimensional and a touch more accurate at a per token cost. This slide is illustrative. It needs an API key, so we don't run it. The important point: the only thing that changes is how the vectors are produced. Everything downstream, normalize, cosine, top k, stays exactly as we wrote it. A few hard-won rules. First and most important, you must embed your query and your documents with the very same model to models produced to incompatible spaces, and comparing across them gives nonsense. Second, if you ever change models, you have to re-embed the entire corpus. Third, embeddings are deterministic for fixed text, so cache them, never pay to re-embed a document that hasn't changed. And finally, bigger vectors usually mean better recall, but they cost more to store and search, a trade-off you'll tune per use case. Be honest about the toy parts. We keep our index in a plain NumPy array in memory, wonderful for thousands of chunks, but it won't scale to millions, and it vanishes the moment the process restarts. There's no persistence, and no way yet to filter by metadata like author or date. Those are exactly the jobs of a real vector database, which we reach in episode 7. But first, in the very next episode, we connect this retriever to the model to answer questions for real. Let's recap. An embedding maps any text to a vector of meaning. Cosine similarity scores how alike two vectors are by their angle, and we built it in a single line of NumPy. Stack those together and you get top case semantic search, embed the corpus once, score everything with one dot product, sort, and slice. We proved it beats keyword matching, and we saw why retrieving the few relevant chunks beats stuffing the whole library. Next episode we take this retriever and build a complete RAG app: load, split, embed, store, retrieve, and feed the result to the model so Atlas answers from your own documents. See you there.